Hey everybody, and welcome to another JASP tutorial video. Today we are going to continue our ANOVA analysis of variance tutorial with repeated measures ANOVA. That's the example we're doing today. Before we get into that, I just want to go ahead and remind you, as always, I am using the current preview build of JASP, which is 0.10.1. And so let's get into it. Okay, I've opened up a file that I found on a lovely website, a repository for several pieces of either real or fake data. This is specifically a simple data set to use to discuss repeated measures. It is very simple, as you can see, only a few variables here. It is test performance as referenced by these values here on a scale from 0 to 100. And the four variables that you see here represent amount of noise. And then we have a gender variable, males and females. And so we are going to ignore the gender variable and the subject variable for this one and just discuss the none, low, medium, and high conditions. And so the assumption that you need to make about this data set is that each of these people did each of these noise conditions and how it and the numbers represent how it impacted their test performance. Okay, so to do repeated measures ANOVA, you click on ANOVA, as I did, and you go to repeated measures ANOVA. And so this opens your setup and your results modules. And you can see this is slightly different from the ANOVAs from the previous two videos, where we just throw in one dependent variable up top and then any of our factors, if it's factorial or just a one factor for a one-way ANOVA. Here we have to set it up a little differently, because how the spreadsheet functions, your data frame is set up here, is that your repeated measures factors, these none, low, medium, and high, also contain your dependent measure, which is test performance in this case. And so how you have to set up a repeated measures factor is slightly different from setting it up, because we technically have four DV values here, four columns that we only have one measure. So how you do this is you label. You start to label. So we have repeated measures factors, and we can have as many as we need. So by default, you need to have at least one repeated measures factor, RM factor 1. Right? This is why it's highlighted in black. And then you need to have at least two levels of that because it needs to be a variable. Now, level 3 and RM factor 2 are sort of grayed out because they are options available to you, but you don't necessarily need to have them. So this is how you set up the structure of your model in this top box, repeated measures factors. In repeated measures cells, this is where the naming from this top box gets edited. So let me go ahead and change that for you. So RM factor 1 is noise level. So that's the noise level. None, low, medium, and high. Okay? And level 1 is going to be none. There's no noise when completing the test. And as I click away from it, you will see down here that level 1 will actually change to the word none. Those two are mapped to each other. And then I'm going to add low here, and I'm going to click to level 3. See, it's grayed out. Once I add medium, which is my third level here, it will add it down to the repeated measures cells. So I'm going to go ahead and hit enter, and I hit enter, and it opened up another available level for me. because I have 4, I definitely need this one. So I'm going to finish by putting high in there and hitting enter. Now when I hit enter, it also added a level 5, but I'm going to ignore that because I don't need it. I don't have 5 levels to this noise level variable, nor do I need to include RM factor 2. So those two things are going to be grayed out. They're actually not a part of the model. The other thing you'll notice here is that the 3rd and 4th levels can be deleted by just easily clicking this little X button here. But you cannot delete the other 2 levels because you can't run the repeated measures ANOVA without 2 levels to at least 1 repeated measures. Again, you're only using repeated measures ANOVA in JASP because you have at least 1 within subjects variable. A variable that one person does all the conditions of, if that makes sense. Even if you have a mixed model, so you have one within subject variable and another between subject variable or factor, you have to use the repeated measures ANOVA module here because you can add in your between subject factor in addition to your repeated measure factor. So this is for RM designs only, or RM only designs, I should say, as well as mixed model factorials. So if I wanted to make this a mixed model example, I would go ahead and put gender over here in a between subject factor because that has to be a between subject factor. Okay, so now that I have my repeated measures factors labeled, I have all of these here, none, low, medium, and high. I can go ahead and grab the particular variables and put them into these blue highlighted cells. So I'm going to go ahead and hit none over here, low, hit the arrow, medium, hit the arrow, high, hit the arrow. Okay. And as you can see, it's starting to run the basic level ANOVA, which is noise level with the residual or error. So we have the source table as we have had in the previous 2 episodes with the ANOVAs that we ran there, the between subject only variables. And we have our sums of squares, our degrees of freedom, the mean squares that we get for dividing sum of squares by the degrees of freedom, mean square of noise level divided by the mean square residual gives us our F value. That F, based on our degrees of freedom of 357, yields a P value, and in this case, it's less than 0.001. Now, if you were running a more complex, as I said, a more complex model that had between subject variables, you would go ahead and put those in this box. And if you had any covariates that you needed to take some variance away to sort of isolate your repeated measure impact, influence, effect on the dependent variable, you would go ahead and put them in here, much like in the previous ANOVA examples that I did here. Okay, although for covariates, I noticed here that they separated ANCOVA from ANOVA. So using ANOVA, you wouldn't be able to put covariates in. And so if you had a covariate, that's what the C stands for, you would put it here, ANCOVA, and it would give you, and that's only if you have a covariate, like age, for example, age, pretestability, which in this case, we could include none as a pretestability, and tested low, medium, and high as the main factor. We could do that. We could do it that way because no noise would be kind of like a pretest in this fictitious data set. So we can do. We can add those things to this more complex modeling field. Okay. So a lot of the things you'll see as options in the RM module look the same as the ANOVA from the previous 2 episodes. So model, we can go ahead and change the model terms that are in here. JASP breaks it up because RM components need to be different from between subject components, because as you can see, we get two different source tables, excuse me. We get two different source tables, and the between subjects effects table gives you just the between subject error, and so you can ignore this one if you only have one RM factor. So it's a one-way repeated measures design, which is what this model is describing, and you can change your sum of squares type here, 1, 2, or 3. Most commonly in social science research is type 2 sums of squares. Here's where you would have your interaction terms if this was a factorial design, etc. So we're going to go ahead and skip that. Assumption checks. Now this is different for RM. Okay, so we have 3 options in the RM module. Homogeneity tests you would only use if you had between subject factors. As you can see, I clicked that one, and it says no between subject factors specified. And so, because I don't have between subject factor, I don't need to check that box, because it's not going to be useful. The reason this option is available to you is if you had a between subject factor. So we're going to ignore it for this example, because I don't need it. But what I do need to check is sphericity. So this gives you Mauchly's test of sphericity. And so the idea with sphericity, it's a hard word to say, but I love it. It's one of my favorite words in all of science and statistics. Sphericity is the repeated measures test of the homogeneity of variances. And so it's the condition where the variance of the differences, so the variance of the differences between pairs, so low and none and low, the variance of the difference between none and low are the same to the variance of the difference between none and medium, none and high, low and medium, low and high, and medium and high. So all of those differences and the variances for those differences should be approximately equal. That's the assumption. Okay. And so we use Mauchly's test of sphericity to determine whether or not that's the case. And again, this is an assumption check, and so this alpha level can be different or the same to the alpha level used for your within subject effects alpha level. So 0.05 would be used for this one. We're clearly well below that. I'll come back to that in a minute. But here we can use the same one, 0.05, or we can 0.01, 0.001, you know, whatever, however conservative you want to be with that test. So W is the value that's produced, and if the p-value is below your alpha, then you have a problem with sphericity and you have violated it. And thus you have to use corrections. And so we can click corrections, and we have 3 checkboxes: none, Greenhouse Geyser, and Hunefeld. These are 2 corrections, Greenhouse Geyser and Hunefeld, or we can have the original test that I had previously if we had violated it. Here's the fun thing, is that we did not violate this test of sphericity, and so we don't actually need the GG or the HF corrections here. You can see these corrections change the degrees of freedom. Even though the sums of squares are the same, the degrees of freedom are different, and thus you end up with a slightly different mean square. But because the mean squares and the residual mean squares don't actually produce an F that's different from no correction, there's no change to our decision. What ultimately would happen is when you are presenting this and you violated sphericity, you would want to use whichever correction you feel comfortable using, and you end up changing the degrees of freedom in your written report. And so instead of 357, it would be 2.49 or 2.50, comma 47.44 if I were to use Greenhouse Geyser. Again, we don't need the corrections, so I can uncheck this box. Now I'm going to close that. Contrasts. Again, if you want more detail about contrast, you can see episode, I actually don't know the number. I'm going to go ahead and put it up in the corner of the screen there. When I first talk about ANOVAs, it's a one-way ANOVA episode. I think that's episode 10 or 9, something like that. So I will skip contrast. Posthoc test. This is important. I have 4 levels of my noise level variable. I have a significant null hypothesis test. I have a huge F. My p-value is less than 0.001, and so I actually need to determine where the difference is in test performance and noise level. So I need to bring these posthoc tests into the fold. And so here I have my pairwise comparisons, okay? And I can get confidence intervals. It gives me my lower and upper for the mean difference between high and low and all of the others. I can get effect size for that. Cohen's D is what's given. I can also pool the error term for repeated measures factors. Since I only have one factor, this isn't going to do anything for me, but if you want to pool the error term from over here, you can go ahead and do that. And then, because these are posthoc tests and I'm running multiple pairwise comparisons, as you can see here, there are 6 pairwise comparisons. I can choose my correction. So we have the Holm, which is by default checked. I could also get Bonferroni, Tukey, and Chaffee as noted here. And as I described in the previous ANOVA video, interesting notes that pop up for this table. 1. Cohen's D does not correct for multiple comparisons. So be careful if you are using effect size measures in reporting your posthoc tests. Tukey corrected p-values are not appropriate for repeated measures test from Maxwell and Field, the information from Maxwell and Field. Chaffee corrected p-values are also not appropriate for repeated measure tests, repeated measure posthoc test. And so they're added as options, but I think Maxwell and Field would argue that it is not a good idea. So we can uncheck that. So really, Holm and Bonferroni are your two corrections here, and this will tell you the p-values associated, because you can use 0.05 and just compare 0.05 to that. And now the Bonferroni also has adjusted confidence intervals for the correction. So we can see that it looks like, using our Holm and Bonferroni, the high versus low, not quite there. I mean, comparing the two p-values, if we go with Holm, then that is a significant difference. Definitely between high and medium. That is, high has a better score than medium sound. High versus none. None seems to do... oh, excuse me, I had that backwards. High versus low is kind of there, Low has a better performance than high. High versus medium, much better performance. High versus none. They're effectively the same, as you can see here. And then the other comparisons are actually quite different. Low versus medium. Low, people do worse. Interesting. Versus medium. Apparently people do best with a medium amount of noise in this data set. Okay, so that's posthoc tests. Descriptive plots, again, we can do noise level on the horizontal axis, and it will give us a line chart. I'm going to go ahead and hit display error bars and standard errors, and I can give this y-axis a label, test performance. Click off of it, and we'll put test performance here, and you can see that the best performing noise level group or situation was medium, so a medium amount of noise. Low must be a little bit too distracting. High also might be very distracting because it's loud, it's uncomfortable, but a medium amount of noise might be useful if you, I don't know, can zone out. So if you like to work in a coffee shop or something like that. So that's descriptive plots. Additional options, we can get marginal means, so I'll go ahead and throw those in. This is what is graphed down here. We can compare, we can bootstrap those means, we can compare marginal means to 0. We can get our descriptive statistics. Of course, we want to go ahead and do that in case we are reporting these means and standard deviations, and we want to make sure that we have the n situation be the same. Of course, there are 20 people in this data set, and so all of these levels have 20 individuals. So means and standard deviations, if you're reporting estimates of effect size, I go into detail about all of these estimates of effect sizes. What I would say for this particular video with respect to repeated measures is partial eta squared and omega squared are generally used for repeated measures situations. Omega squared is perhaps the most useful, and you can see that it is slightly more conservative effect size than partial eta squared. These effect size options, eta squared, general eta squared, and partial eta squared, are also there to be available for your between subject variables. But I would say if you have omega squared, report omega squared for your RM factor. So here we see that the omega squared value is 0.588. So 58% of the variance in test score can be attributed to noise level, the noise level variable. Okay. We don't have any interaction terms, so no simple effects. And then if I needed to, I could use the non-parametric tests over here. I'm just going to go ahead and throw it in and show you it's the Friedman test. And so it gives you a chi-square as opposed to F. And you will get Kendall's W from that. And you can use Conover's posthoc test in addition to the Friedman test if you run against violations of ANOVA. You might want to check for normality, and if the issue with normality is problematic, then you might want to use Friedman test, or if you want to use repeated measures ANOVA on an ordinal scale RM factor as opposed to a continuous scale like this. Okay, so that is basic repeated measure ANOVA in JASP. So that's going to do it for this tutorial. Please leave your comments and feedback down below. Thanks for watching. Bye-bye.